What we do is we characterize nanomaterials. So if you have a material, you make it very small, behaves differently from the bulk. But in order to understand why it behaves the way it does, you need to know the precise arrangement of the atoms. And Brookhaven has this amazing facility, which is this very intense synchrotron X-ray source. There's an electron ring, which is about 1 kilometer in length. What we're interested in is when the electrons fly around the ring, X-rays come flying out. This gives us a very powerful probe of the material. So right now we're in the storage ring tunnel at NSLS2. This is where the X-rays are made, the intense X-rays that we use for our experiments. So inside this tube, when the machine is turned on, there are bunches of electrons that are flying at nearly the speed of light. The X-rays fly in a straight line. They deviate from the electrons. They go in a straight line through that hole in the wall to the beam line where we do our experiments. They go through this concrete wall and they come into this lead-lined hutch. So the X-rays are coming from down there and they're flying up this way. And each of these different components is doing a different thing to the beam so that when it emerges in the experiment hutch, it's exactly the way we want it. This is where we do our experiments. This is a fully instrumented hutch ready for collecting data. The X-rays hit the sample, they scatter off the atoms, and then they form a pattern on the detector. So the X-rays scattering off the atoms let us see exactly where the atoms are in the material. We look at pharmaceutical materials, batteries, catalysts, photovoltaics, high-temperature superconductors, which are very exotic electronic materials. The whole thing that we're trying to do is link structure to the behavior, because the behavior of a material depends very sensitively on the structure, the atomic arrangement. If you're building a window, the property you want is you want it to be transparent. But actually, we would like smart windows that when it's really hot outside, they cut off infrared light, which is heat-containing light. But in the winter, when it's really cold outside, we want them to let the infrared light through. Once you start thinking like that, then you think, wow, what material would do that? I mean, it's kind of like a painting. If you think of a painting, right, and you put down dots of different color, so like the pointillist painters, you get very close to the painting, what you see is a blue dot and a red dot and a green dot. But then you step back from the painting and you see people picnicking at a river. If we can, number one, design the little dots and their color, and if we can also arrange them, we can get that kind of richness of material design space